Hello, hello. This is Simone Bertoni, and today I want to show you the online Bode Plot Generator that I built and I embedded in my website. So let's dive in. Okay, so this is my website. You can go to Bode Plot Generator, and there is a lot of explanation here. The tool will pop up, and there is a lot of explanation of what is about the plot and what it does for you and how it can help you. But now we'll go through it anyway. So first, there are two main reasons you might want to use a Bode Plot Generator. Okay, so one is if you want to do an open loop analysis of your plant, your system. So you want to see the frequency response, as simple as that. So not really much to do with controls, but you might want to see how it amplifies the signals, how it will change the phase and all that part. Okay, so we can have a look at that because you can do that too. So let's say that here we type the function, okay? Very simple typing, as you normally do fundamentally, okay? There's nothing strange. You have a little pop-up here telling you that you can only use digits and the expected mathematical symbols, okay? So let's take a function that has some like a peak, okay? Let's say something like this. And maybe we make the gain 1. Yeah. Okay, then we hit enter when you're ready, okay? And if you do something wrong, like, I don't know, using the wrong symbol, it will tell you that you got it wrong, okay? And it won't draw anything. Okay, so what it's telling us so that the margins here and the closed loop analysis is for control. So we're not talking about that now. So this is just showing you the Bode diagram, right? And you can see that you have what the phase does, and you can see that you have a big peak. So your system will amplify all the components around this frequency, okay? Which is 10 radians per second. And this is the kind of analysis you can do in open loop. And I'm not probably the best person to explain that, but if you're going to use it for that, you know what you want to do. Okay, so that's the first reason. Then the second reason is more for controls. Okay, and for controls, we use it because in the case where your plant is stable and your controller obviously should be stable as well, then the loop transfer function, which is defined as the controller transfer function times the plant transfer function, is when this is all stable, you can use that function. So we will call it G in this case. It's called G in all the explanation here. You can use that in the Bode diagram, and it's a simplified proxy to look at the Nyquist theorem, basically. So you can see what is if your closed loop is stable or not, and it will tell you. Okay, so let's have a look. Let's take first the case where we use an unstable system, okay, an unstable plant. So let's say our plant is this, okay. So if our plant is this and our controller is 1, essentially, okay, in this example, because I'm not adding any controller. So there is a feedback loop which is only proportional, and the gain is 1. And this is your plan. Okay. It's telling you that the loop function is unstable and also the closed loop system is unstable. Okay, so there's not really anything to say in this case. It's drawing the body diagram, but it doesn't mean anything. So let's try to change. Let's say we add a controller that has gain 10. Okay, so in this case, it's telling us that G is still stable, but the closed loop system now is stable. Okay, so that's a very different case, and this is as much as it can do. Okay, in this tool, in this scenario of the unstable plant. So now we can see what is more relevant, because I think it's much more relevant when everything is stable and you do your classical analysis on body. So let's take, what function can we use now? Okay, let's see something like this. Yeah, this. Okay, so this is in this case, this closed loop system is stable. The controller at this time is 1. Okay, again, there's no controller, so it's like a unit gain. And it's showing us some margins in this case, okay, for the stability of the system. And I think if we change the function like this, it's a little bit more helpful, because we can see that in this case the closed loop system is unstable. Okay, and we can make it stable. So you see that we are crossing the gain, the magnitude 0. We are crossing it when the phase has already gone below minus 180, essentially. So what we can do here is we can bring the phase up using a 0 around that frequency, and then use a pole bit more higher frequency. Okay, so let's try to do that. So this is the controller now, and I'm going to try this. Okay, so now the closed loop system is stable. We kind of shifted the phase a bit more to the right, and we are crossing before when the phase has gone below minus 1 or 180. Okay. Now what we have here, stability gains. Okay. So stability gains, there is a good, let's take a look at the explanation here just to keep it for us. I'll go to the sensitivity margin as last one because it's less known, I think. The gain margin is simply how much you can increase or decrease the gain of the loop before the closed loop system becomes unstable. Okay, so in this case, you can see that it's telling us 26 dB at 14 radians per second. Okay, because we cross the phase here around 13.7. So this calculation is more accurate. So than my mouse, obviously. So it's this point, okay. And here you can see that you are at minus 26 dB more or less. So this is the margin essentially. This bit here between this line and 0. Then we can see the phase margin is the same thing, but with phase. Okay, so how much shift we can tolerate before we become unstable. And that is measured where the gain is 1 in absolute terms or 0 in dB. So we're here, we can see that we are around minus 140-ish, and we have 35 degrees before we get to minus 180. And then the sensitivity margin is an interesting one. Okay, it's a very important one. It's a less known one, but it's arguably the most important. Okay, and it's the distance between the Nyquist plot and the point -1 of the on the real axis. Okay, which means how far we are from circling the -1 point on the real axis. And that's very important. It captures, there are cases where your system can have very good phase margin, very good gain margin, but it's still getting close. Okay, they are strange cases, but there are such cases, and this is capturing everything essentially. Okay, so it's not getting fooled by these cases. So the sensitivity margin is the distance, and you can normally say that zero point 0.5, zero point 0.6 is a good margin. Okay, it's less defined than gain margin and phase margin. But generally 0 0.5, 0 0.6 is a good number. If you start having 0 0.2, 0 0.1, that's very close to instability. So we can see here if we let's see. Yeah. So I've increased the gain, and now we're getting much closer to instability, right? 6 dB gain margin, 5 degrees phase margin, and 0.1 sensitivity margin. So that's what it's another indicator that will help you. Okay. Then one more thing on the margins, the delay margin. Okay, this is another very interesting margin which I think is used not enough, and it's very helpful again. It's how much pure time delay you can tolerate in the loop before you go unstable. Okay, so it's a friend in a way of the phase margin. It's essentially the phase margin in radians divided by the frequency where you get the phase margin in radians per second. Okay, and then you get seconds. But what it's telling us is if you have a communication delay, for example, in your loop, so you might have that you have a controller that is reading a temperature, a distance, whatever you're controlling is reading it at a certain point and is passing on. It's actuating it's controlling the actuator half a second later, okay, because of your program, because of your loop, whatever, I don't know, okay. But you know you have that kind of delay, and you normally have some. This loop is telling you that you can tolerate maximum 0.2 seconds delay in that loop. If you have more, you will be unstable. And I think this gives a bit more, it's slightly more practical view of what you can, or what that means, okay? Because phase delay, phase margin sometimes is a bit like, oh, what does that mean? So this is another helpful indicator. Okay, the last thing is that you can determine the range. Okay, it doesn't really pick up the range of frequencies automatically, so you need to tell it what you want. By default, is set to between 1,000 radians per second and 0.001 radians per second, but you can change it. And the reason is that, let's say that your function is very shifted toward high frequencies, right? So you might have something like this, and then we put something even bigger, okay? Something like that. So clearly now we are not really capturing what we want here, okay? We're not seeing what's happening where we need. So for example, we don't care to go to that low frequencies now, but we need much higher frequencies. Okay, so that's, and now you can see where you want to see your plot. Okay, I think this is what you can do with that feature. Okay, that's everything. Obviously, you have my course on PID control if you want to take a look, if you're interested. It's 15% off. So have a go if you're ready. But most importantly, thank you for watching. I'll see you in the next video.